this is my recap of the complementary relationship. So, just like transposition or inversion, a complementary relationship is something that two groups of notes can have. It's pretty simple. You have a chord that has whatever notes it has in it. Its complement is going to be made up of all of the notes that are not in the original set. A very simple example of that is the white keys of the piano and the black keys. So we have a C major diatonic collection in the white keys. Versus the black keys, which is an F sharp major pentatonic. So you can hear orally those two sounds are linked, and what that sound is the complementary relationship. That example is a complementary relationship at its most simple, right? It's what we would call a direct complementary relationship, where you have notes and then all the other notes. No overlap. Every pitch class is covered, right? And so a C major collection, that's a septichord, and the F sharp one is a pentachord. So a way that we can tell that those fill out all of our pitch classes, or something that maybe points us in that direction, is that penta, septa, 5 plus 7 is 12, right? So all of our pitch classes are covered because we have 12 unique ones. That is, like I said, a complementary relationship at its most simple. That also means that it is one of the less common ways that we'll see it. What's more common is what we would call an abstract complementary relationship. So to do that, I have some repertoire that we can look into, that we can analyze together. And this comes from Halsey Stevens' Sonata for Trumpet. This is the third movement of that. I'm going to play two short selections, and then we can take a look at those pitch classes together. That's our first set. And that's the second set. So, if we take a look at the first set and we map those onto a pitch clock, what we get is D flat, E flat, F, A flat, and B flat. That gives us an INF of 2, 2, 2, 3, 2, 3, and an IV of 0, 3, 2, 1, 4, 0. If I were to take every note that's not found in that original pentachord, those notes would be C, D, E, F sharp, G, A, and B. Those have an INF of 1, 2, 2, 1, 2, 2, 2. Let me play those for you so you can hear those, how they would sound next to one another. Here's our original collection. And those pitches I was saying were written pitches. This is our original collection. And its complement would be this. But that's not what we get in the piece itself. What we get is a collection C, D, E flat is what you would have heard if I hadn't missed that note, F, G, A, and B flat. All right? So obviously some of those notes are different, but if we look at the INF, we get 1, 2, 2, 1, 2, 2, 2, and if we look at the interval vectors, those are the exact same as well. So what we have is a transposition of the complement of our original section. This is an example of what we were talking about as the abstract complementary relationship. The reason why this is still auditory and the reason why this matters is because if we look at the interval vectors for these two respective chords, Our original one has an interval vector of 0, 3, 2, 1, 4, 0. And your second chord, the complement of it, or the transposition of its complement, has an interval vector of 2, 5, 4, 3, 6, 1. If you look at those numbers, ignoring the last set, all of these are different by a factor of 2. Right, so our septichord is always going to be 2 higher than the digit for the original pentachord. That mathematical relationship between those chords is what makes this relationship auditory. It's what makes it significant to us musically. The way that we find what the difference between those interval vectors is by taking the difference in the number of notes between the two chords. Our original was a pentachord. Our next one was a septichord. That difference of 2 is going to be the difference between each digit of our interval vector, with the exception of the last one. The reason why the last one is different is because 6 is our largest interval, and it perfectly, evenly splits the octave. Because of that, and because of weird math things that go along with that, our sixth digit of the interval vector is going to take whatever our difference for all of our other pitches were and divide that by 2. So, pentachord, septichord, our difference was 2. All of these are different by a factor of 2. So our last one is going to be different by a factor of 2 divided by 2, which is 1. And this relationship is going to be true for any kind of complements that you find. Right, so if you're ever trying to write out a complement or something, you can look on the INF table, and those will always be across from each other. And their IVs will always be different by a factor of however different they are. If you have a trichord and a nonochord, it'll be 6. With the pentachord and the septichord, like we just did, it'll be 2. And that'll always be the case. One cool thing is with hexachords, you can actually have something not only be a complement of it, but be a transposition of the original set as well, right? Anything with 6 seems to get a little funky in the kind of analysis we do. But that's about everything I can tell you about complementary chords. Thank you for listening and have a wonderful day.